Dear students, what we discuss in this class is the coefficient of determination. The coefficient of determination. In the previous class, we have discussed how to estimate a simple linear regression model, and we have also introduced an example. Using data, the estimated regression line was y hat equals minus 2.26x. This is the estimated equation for the data age and price of cars, where x is age in years and y is the predicted price in hundreds of dollars. Now suppose that we want to predict the price of a car which is 4 years old. So we substitute the value here, 195.47 minus 2.26 into 4. The predicted value is equal to 114.43 in hundreds of dollars, or is equal to $11,443. That is the predicted price of a car which is 4 years old. Now we have to consider two issues. One is, how valuable are such predictions? The second is the regression equation useful for predicting the price? Two issues here. Is the regression equation useful for predicting the price? The second is, how valuable is or how useful is the prediction? These are the two issues which we discuss once we estimate a regression model. Now, there are several methods to evaluate the utility of a regression equation for making prediction. There are several methods existing to evaluate the utility of a regression equation for making predictions. One method determines the percentage of the variation in the observed values of the response variable explained by the regression or the predictor variable. Of the several methods for evaluating the usefulness of a regression equation for making predictions, one method determines the percentage of the variation in the dependent variable or the response variable that is explained by the regression model, explained by the predictor variable. Now, in order to find out this percentage, that is the percentage of the variation in y explained by x, we define two measures of variation. We define two measures of variation. One is total variation in the observed values of the regressant, the response variable, the dependent variable. total variation in the observed values of the dependent variable, the regressor. The second is the amount of the variation in the observed values of the response variable explained by the regression. That is the proportion of the variation in y explained by the regression or explained by x. So we consider two variations. One is total variation in y, the response variable. Second is the part of the variation in response variable explained by the regression, explained by the predictor variable. Now, to measure the total variation in observed values of the response variable, we use the sum of squared deviations of observed values from the mean of that variable. To measure the total variation, we use the sum of squared deviations of observed values of the response variable from the mean of those values. And this measure of variation is called total sum of squares. This measure of variation is called total sum of squares. We write it as SST, and SST is sigma of yi minus y bar square. Total variation, SST, sigma yi minus y bar square. If you divide this quantity with n minus 1, n minus 1 is the degrees of freedom, you will get the sample variance. So SST measures total variance, total variation in the observed values of the response variable. Dividing this with the n minus 1 will give you the sample variance. Let us see these things in the form of a graph. Now, let us, this is yi, y hat I, y bar, and this is a point, say xi, yi. Now this, so suppose that this is a point xi, yi. Now the total variation is given by this distance yi minus y bar. Total variation yi minus y bar. Then this distance is yi minus y hat I. And what is this distance? This distance is y hat I minus y bar. This distance. Now, so this is the total variation. To measure the amount of variation in the observed values of the response variable explained by regression, you consider a particular point xi, yi. Now, the total variation in the observed values of the response variable is yi minus y bar. And this yi minus y bar is divided into two parts. Total is yi minus y bar. It consists of two parts. One is the deviations, the variations explained by the regression line. That is y hat minus y bar. The other part is unexplained deviation, that is y hat yi minus y hat. So y hat minus y bar and yi minus y hat. So yi minus y bar, total variation in the observed values of the response variable is divided into part of the variation explained by the regression line and the part of the variation not explained. Now, the amount of variation in the observed values of the response variable explained by the regression line is sigma yi minus y bar square. Sigma yi minus y bar square. Sorry, sigma y hat minus y bar square, and we call this regression sum of squares. This is SST, sum of squares regression. This is regression sum of squares, SSR. So SSR is sigma y hat minus y bar square. We take deviations, square each deviation, take a sum. Now, using the total sum of squares and also the regression sum of squares, now we can determine the percentage of the variation in the percentage of variation in observed values of the response variable, that is explained by regression as SSR by SST. SSR by SST. So, this quantity is known as coefficient of determination. So, R square. R square is coefficient of determination, SSR by SST. So, coefficient of determination is the proportion of the variation in the response variable, proportion of the variation in the observed values of the response variable explained by the regression, or it is the percentage of the variation in y explained by x. That is the definition of coefficient of variation. Now, before applying the coefficient of determination, this is known as the coefficient of determination, not variance. Now, before applying the coefficient of determination, let us consider the remaining deviation. That is the part of the variation in y not explained by the regression line. We call this error sum of squares. Sum of squares, error sum of squares, that is yi minus y hat. Take all the deviations, take sum, square it, sigma yi minus y hat square. The amount of variation in y that is not explained by regression, it is known as error sum of squares, and SST is equal to total sum of squares is equal to regression sum of squares plus error sum of squares. SST is equal to SSR plus SSE. Now, this is R square, and R square always lie between 0 and 1. That is the range of R square. R square 1 means, R square is equal to 1 means regression equation is quite useful for making predictions. R square 1 means all the observations will lie on the regression line. It is quite useful. R square 0 means regression line is not useful for making predictions. Typically, R square lie between 0 and 1. Typically, R square lie between 0 and 1. 1 or close to 1 means regression equation is quite useful for making prediction. 0 or close to 0 means regression equation is not very useful for making predictions. Now, Using this identity, SST is equal to SSR plus SSE, we can write R square SSR by SST also as equal to as SSR is equal to SST minus SSE by SST. So is equal to 1 minus SSE by SST, that is R square. R square can also be written as 1 minus error sum of squares by total sum of squares. So this is R square, coefficient of determination, the percentage of the variation in the observed values of the response variable explained by the regression line. Now, let us see what are the computing formulas. SST, SSR and SSE are the defining formulas for R square. Now, let us see. So, R square is equal to SSE by SST is equal to 1 minus SSE by SST. These are the defining formulas. For computing the sum of squares, such computations are not required nowadays because all these values will be automatically computed by the software. Anyway, the computing formulas are SST is equal to sigma y square minus sigma y square by all square by n, something which we have already defined. Now SSR is equal to sigma xy minus sigma x into sigma y by n square divided by sigma x square minus sigma x the whole square by n, and SSE is equal to SST minus SSR. In the example of the price and age of cars, the R square value obtained is 0.853. 0.853. That is 85.3% of the variation in the observed values of the response variable is explained by the regression line. The remaining 14.7% is unexplained variation in the observed values of the response variable, and it may be due to factors other than age of the car, that is coefficient of determination.